Here we will see how the locality sensitive Hessian or simply LSH is implemented through cosine similarity. So first going to discuss about this concept. First we have to recap something about cosine similarity. We already learned what is the cosine similarity. Just to recap these things. So cosine similarity is what? It is simple nothing, just it is the similarity between the angle similarity. Suppose let's take it's our axis, and suppose let's take here we have two vectors x1 and x2, two data points, and this is the corresponding direction vectors of these data points. And suppose let's take we have another data points x3 here, another data point. Okay, and if you just see this thing, the cosine similarity between x1 x2, suppose let's take the cosine similarity between x1 and x2, angle between x1 and x2, between angle these two is equals to theta 1 2. Let's take theta 1 2, and the angle between, suppose let's take we have another set of points, suppose let's take x4 is here. Suppose let's take our x4 is here, and the angle between x1 and x4 is this I call the x14. So the cosine similarity of x1 and x2 means what? This thing simple, cos of theta 1 2, and the cosine similarity of x13 is what? Cosine similarity of x1 and x3 is, this is the nothing. In if you just see the angular distance, angular similarity is nothing. They have the nothing, no nothing in the same angle they appear. So cos 0 means simple 1. It's the cosine similarity 1. So the simple thing is that if this cosine similarity means angular, one kind of, you can conclude this thing one kind of angular similarity. Cosine similarity is equivalent to angular similarity. Both are the same kind of, and the relations is like that. If our angular distance means theta, if we increase the angular distance, means the angular distance, this is mean what? This implies that if we increase the value of angular sign, then what happen? Then the cosine similarity is decreased. Okay, if we increase the value of theta, or simply x1 and x2, two vectors, if we increase are angularly increased, that implies its distance is increased. I'm talking about the angular distance. Angular distance is increased. This implies simply its cosine similarity is decreased. This is the simple relationships. We already know these things from the previous lectures, one of our previous lectures. And relations and similarity is like that. If our similarity increases, if we increase the similarity, this implies that our distance decreases. If we increase our similarity, then our distance decreases. So this is the simple relationships. between the angular similarity and means angular similarity same kind of cosine similarity. This is the simple. Okay. Now let's see how the locality sensitive hashing is relate how this cosine similarity we can implement for a locality sensitive hashing. Okay, let's see. So first what is actual locality sensitive hashing? First recap this thing. So locality sensitive hashing, suppose we have two features vector. Let's take it is one features, it is another features, and we have two vectors. Let's take we have x1 vector and x2 vector is here. This is our x1 vector, this is our x2 vector, and the angle between x1 and x2 is theta 1 2. Okay, and suppose let's take another vector is here in this directions, another vector x3 is here, and the angle between x1 and x3 is theta 1 3. Let's take theta 1 3. So the if we angular distance is increased, just see this thing, if our angular distance is increased, our cosine similarity decreased. So so in such scenario our hash value will be what? So just recap this thing. So actually our hashing is something, hashing is a like a table. In one column we store the key and another column we store the value, its value, corresponding value. So if our theta 1, if our theta are approximately equals to 0, if theta is so small, suppose let's take our theta is approximately equals to 0, this means what? This means our both the vectors are similar or the close vector. So if our theta is 0, then we can conclude that if theta is approximately equals to 0, then from here we can conclude that x1 and x2 are similar, or it is a close vector, or it is a close vector. So now the main question is, for such kind of similarity, for such kind of cosine similarity, how we calculate the hash value? So the how to calculate the hash value of x1, how to calculate the hash value of x2, hash value of x3. This is the main questions. How to calculate it, this hash value that will be stored in such bucket. We have already seen this thing, this cell is called the bucket. Main question is how to find this hash value to store this bucket. So let's see. So one thing before going to start, one thing, LIC is simply a randomized algorithm. First thing, this thing is have to remember, it is a randomized algorithm. It is simple a randomized algorithm, first one. And what is actual means about randomized algorithms? Randomized algorithms means it will not always give the correct answer. Means suppose if an algorithm is not randomized, if such many times we have run these algorithms, these algorithms gives the same result. But in case of randomized algorithms, various times it give various results. Okay, means we cannot expect the appropriate results from this kind of algorithms. We cannot expect, means I will not always give, means it will not always give you the correct answer. It it will not give you the correct answer always. Okay, and the next thing is probability of the correct answer is high. For this kind of randomized algorithms, we can add the concept probability. So we can the probability to give the correct answer is high, but not properly it will give the correct answers always. Okay, so the probability it will give the correct answer each high. Okay, its probability is high to give the correct answer. Okay, so let's see how this thing is actually work. Let's see. Suppose let's take we have two features of data points. Suppose let's take we have two features of data points. Just for simplicity we are using two features. Suppose it is features 1, it is features 2. Let's take, and let's take this from this plane we can randomly select one line that will in 2D we call line, in 3D we can call plane, and in higher dimensions ND we can call this is a hyperplane. So suppose let's take we can randomly selected one line. Suppose let's take this is the one random line that will separate our whole plane in two parts. Suppose let's take one vector is lie on this side. Let's take x1 and another vector is lying on this side. Let's x2 and this plane that we selected this plane randomly, this plane is pi plane. This plane is called the pi plane. So first one concept, this is called the randomized algorithm. So because here we have selected this plane randomly. So because of this, because we've selected random hyperplane. Here we have selected the plane, it is randomly selected. And let's assume this plane is passing through origin. Let's take this plane is passing through origins. If a plane is passing through origins, so the equations of such plane will be x transpose x is equals to 0, where w transpose x is equals to 0, where w will be the normal to the plane. W will be the normal to the plane. Okay, means what is the actual w here look like here, this kind of, here our w will be look like this, this is the, if this is a pi plane then w will be look like this. Okay, so if w will be look like this and it is simply normal to the normal to the plane, and in such scenario, so what will be the multiplications of w transpose x1? I think you will already know this kind of concept in your undergrad levels or in 12th standard. So what will be the value of w transpose x1? Because the directions of w and the directions of the x1, you will see the same side of the plane. So this value will be greater than is equals to 0. And what will be the value of x2? Because the directions of the w and the directions of the x2 is the opposite side of the plane, so this value will be w transpose x2, its value will be less than 0, less than equals to 0. Okay, less than equals to 0. And now the main thing is that how to choose actually for w is what, if you consider a higher dimensional plane, if we consider the higher dimensional space, so w will be a simple suppose if we consider the d dimensional, suppose let's take let we consider the d dimensional space. So in such cases w will be a d dimensional vector, w will be look like that. this kind of index 1 2 3 1 0 1 2 and d minus 1. If we just consider the index from 0, then it will be d minus 1. So there have some values. That's just we have chosen this value randomly. And one thing, w here, w is the normal plane, as well as it is the unit normal plane to our plane. This is a unit normal vector to the plane pi. Okay, this thing we have to first remember. W is simply a unit normal vector, that is simple normal to a plane pi, and w is the also a d-dimensional vector. Okay, this is the, if we consider this plane for easy of simplicity, we have considered this line, or this line is passing through our origins. If it is not passing through origins, in such cases we have considered the plane, the hyperplane will be look like this. Thus b is equals to 0. Okay, if so, here b is the interceptor term, b will be the interceptor term to our axis. So just for simplicity our calculations, we have omit this we have not taken this kind of situations because of simplicity of our calculations. If you interested add the b term, then the same calculation, same thing will be easily you can calculate it. So because of simple simplifications of our calculations, I am taking here w transpose x is equals to 0. Just simple, I am considering the hyperplane will be passing through origins. So in such cases, the plane will divided our spaces in two sides. This is our one side, this side is one side, this side is one side, and this side another side. Okay, for one hyperplane we divided our plane, divide our hyperplane in two sides. So if we take one hyperplane, then we divide our whole space into two sides. Okay, now let's see. And the main thing to draw this kind of hyperplane, how we will draw this hyperplane, just we have to choose such vector w randomly. We have to choose this vector w randomly. We have to choose this vector. Now how to choose randomly? So if you know, I think you were already know the Python language. So in Python language, in NumPy library, you can easily call this a w dimensional vector. So how? Suppose we are interested to find the w vector look like this. W vector, we are interested to find w. So w will be simple. We have to quote w NumPy. Then we have to generate the random value, random dot how this distributions of the random, we have taken the normal distributions. Normal of the its mean will be 0 and its standard deviations will be 1. Random and randomly we have generated, and from the normal distributions, its mean, its standard deviations, and how many dimensions we needed. Here we have considered, suppose let's take d dimension. Just simple, we have to code this thing. So then it will automatically generated the w vector randomly from these distributions. Okay, I think we have not repeat this thing, normal, what is normal, how to generate. I'm just memorize this thing, how to generate the normal random vectors from these distributions. Okay, this is the simple thing. So then easily we can construct the random hyperplane. Suppose the main concept is here. If we just taken one hyperplane, then we divided our whole space in two sides. If we just take on here the same thing, if we'll take on, if we just take, just see this thing pictorially. If we take one hyperplane, let's take it is pi 1, then it's divided two sides. If we take two hyperplane, suppose let's take it's another hyperplane pi 2, then how much sides? One side, two side, three, four. If we take another hyperplane like that, pi 3, then how much sides? And just think this thing as a pizza plate. Just we have slicing the whole pizza plate as like that. The random hyperplane will be doing the same jobs. As many hyperplane you can consider, our space will be slicing. So the number of slicing of our space will be increased. Okay, so simple, the conclusion is that if the number of hyperplane, if the number of hyperplane is increased, then the conclusion is that number of slice of the space will increase. Okay, this is the sample relation. now come to the main concept. Suppose let's take, so this thing will be very interesting. Suppose let's take, I think it will be better if we take it for, suppose let's take it's our whole space. Okay, and in this space we are interested to divide this space as to this plane. Suppose let's take it's one hyperplane, let's take it's another hyperplane, and let's take, I am considering another hyperplane in such directions. Okay, in such direction. Suppose let's take it's a pi 1. Let's take this hyperplane is the pi 1 hyperplane, green one is the pi 2 hyperplane, green one is the pi 1. I have to rename very carefully. Okay, pi 1, this orange one is the pi 2, and green one, let's take it's the pi 3 hyperplane. And the normal of this hyperplane, normal of the pi 1 hyperplane is the, let's take its normal value will be w1. Its normal of the to the hyperplane is, let's take it's the normal to the hyperplane is w2, and its normal vector to the hyperplane is w3. Let's take this is the normal vector to the hyperplane. The three hyperplane we have considered. So how many slicing we have divided our whole space? So this is the first slice, second slice, fourth slice, fifth, sixth. 1 2 1 1 2 3 4 5 6 6, I think 6, yeah, 1 2 3 4 5 6 6 spaces, 6 slicing. We have just divided our whole space in six slice. Okay, now here the concept is, suppose this is the one side, so this is the one side, this is the one slice, this is the another slice, this is the another slice, this is another one, this will be another one, this will be another. So this is the slide. Suppose let's take our points are distributions in our whole space. I am using the point red color. Suppose let's take here we have some point, and here we have some point. Here we have some point. So we am considering this chunk of points in one class, in one cluster. This we have considering this this chunk of points. We have considering this chunk of points in one cluster, and clusters is named as like that. So suppose let's take this is the cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, cluster 6. So this is one cluster, this is another. Suppose let's take, we have taken all the points here in this cluster, another points is in this cluster. Okay, now the questions is how to find the hash value of each cluster. This is the main question. Okay, let's see. So suppose let's take here our point is, I think if we rename this point it will be better. Suppose let's take our point is here in this cluster. Our point is, suppose let's take x1, x2, x3, x4, x5. Let's take here we have x5 point, and in this cluster we have another x6, x7, x8, x9, x10. Suppose let's take here we have 5 points, here I have 5, here 1 to 5, we have 6 to 10. We have points in this cluster 1 and in cluster 3. Just I am considering the two cluster only. So in this cluster, in the, just if you see the first cluster, in first cluster, what, suppose now what will be the value? Just consider the first pi 1 plane. Just if you multiply w1 transpose x1, so what will be the value? w1 transpose x1. So the directions of the w1 and all the clusters value. So instead of using w1, I am using xi. w1 of xi will be greater than is equals to 0, where I is from 1 to 5. 1 to 5. Okay. Similarly, for this plane, just see this point, and for this point also, w1 transpose xi is also greater than. It's for just one thing we have to remember. If it is the greater than is equals to 0, then we have taken 1. If it is less than 0, then we have taken -1 for binary classes. Okay. So what will be their value here? Area will be +1. Similarly for here it will be +1, and for here I will be from 6, 7, 8, 9, 10. Okay. Now consider this side w2. So w2 transpose x I will be similarly what? Just see the directions. W2 directions is always here, and the w2 of this point, just see, it will be 1. Okay, it will be 1 because the directions of the w2 and all the points from I is equals to 1, 2 to 5 the same directions, but w2 transpose xi will be -1. For what I? Its I will be 6 to 10. This side, because the w2 direction is this side, just see the w2 plane, just pi2 plane, the pi2 plane, w2 direction is this side, where the plane does the point of these x2 to x10 is in this side. This value will be -1. Now consider w3 plane. w3xi will be what? w3xi, if I is from 1 to 5, then the same directions, so this value will be +1, where I is equals to 1 to 5. And the w3 transpose xi will be what? Xi means in these directions xi I, so this value will be -1. So I is from 6, 7 to 10. I think you have understand. Just I am using this thing, just I am using this concept, primary this concept, directions, nothing else. Okay, this concept. So the number of just now the hash value will be in this plane. So here how much plane we have considered here? Here we have considered the 3 planes. So here our T number of hyperplanes. So here number of hyperplanes is what in such example? Hyperplane is 3 in this example. So the key value of this slice of this chunk 1 is 3. The key value will be 3 corresponding vector. So for what? For this chunk. So in this chunks how many point? 1 2 5. So just see. So this value will be first for this is for w1 plane, this is sorry pi 1 plane, this first value for pi 1 plane, this value for pi 2 plane, this value for pi 3 plane. Okay, and for pi 1 plane this value is for what? This value is 1, and for pi 2 plane this value is also 1, but for pi 3 plane this value is also 1. Okay, I think you have understand. If we have n dimensions instead of 3, if we have m dimensional hyperplane, if you have m hyperplane, then the key value of the hash functions of will be m dimensional vector, will be m dimensional vector. Okay. So now let's see what will be the key value of this chunk, means chunk 3. In this chunk, so what will be the key value? So the key value will be in these chunks, just take 6 to 10. So first for w1 this value is 1, for w2 this value is -1, for w3 also this value is minus. I think you have understand this thing, how to calculate the key value for each chunk of vectors. I am using the concept, this concept here. So the for each point, here, so for hash value of, so the hash value of, suppose if you take any point, suppose let's take I am taking here x2, so this value will be what? 1 1 for each point. So the hash value, just simplify, so the hash value of xi will be 1 1 1, where I is coming from 1 2 3 up to 5, and the hash value of xi will be 1 minus 1, where I is going from 6 7 to 8 10, 6 7 to 10. Okay, just simple relationships that we have made. And for a slicing, the same things we all done for this slice. For this slice we can easily construct the key hash value. For this slice also we can construct the hash value. For this slice, for each slice we can easily construct the hash value. Okay, I think you have understood. You can easily do these jobs. Just as a homework you can do this. Okay, now we have to remember one thing. So the hash of x, so the simple formula of our hash functions will be, so hash value of x will be like that. Suppose let's take our m is equals to number of hyperplanes. This is the general formula. Number of hyperplanes. If this formula is number of hyperplanes, so the hash value will be our n dimensional. So the hash value will be n dimensional, 0 1 2 3 dot 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 to m. And this value and this value will be what? This value will be sine of w1 transpose. This is for responsible for pi 1 plane, this is responsible for pi 2 plane, this is pi 3 plane, this is responsible for pi m plane. This value will be sine of, this value will be sine of w1 transpose x. This value will be sine of w2 transpose x. Only this value will be sine of wm transpose x. Okay, This is the sample. Okay. So here we have seen that how to construct the hash value. We have already seen from here how to construct. Now the thing is that how to construct the hash table. This is the main thing here. How to construct the hash table. So let's see. So our hash table is look like that, or if you just see our hash tables is look like that. Here we have stored the key and here we have stored the value, and this is one bucket. This is bucket 1, this is bucket 2, and this is bucket M. Let's take. So here bucket will be the number of slides. Just here in such hash table, here bucket will be the number of slices. So here how many slices? If we take the number of hyperplanes is equals to 3, then how many slices we have make? For these cases we have make the 6 slices. So in such cases in these examples, thus this M value will be 6. Simple. This M value is this simple 6. This M value will be 6, and the key value will be what? This in these cases key value will be the tuple of number. This tuple of number will be the key value. So if the key value is, and if this key value is 111, suppose let's take we have key value is 111, different color. Suppose let's take our key value is 111. So in such cases the key is 111. If key is 111, suppose for this square, if key is 1, what will be the value here? So here our value will be x1, x2, x3, x4, x5. Okay, if suppose this, if you consider this plane here, what is the actual what is the actually key value? 1 minus 1 minus 1. If our key value is 1 minus 1 minus 1, then what will be the value for this key? 1 minus 1 minus 1, our value will be x6, x7, x8, x9, x10. Okay, so now the question is, what is the actual time and space to construct this table, to construct this hash table? This is called the simply hash table. What will be the time and space to construct this hash table? So the simple space will be, so space will be how much? So because we suppose let's take we have n point, we have suppose total number of point is n and each point is d dimensional, because here we have considered the large dimension for the locality sensitive hashing. Because of that, for handle the large dimensional data points we have used the locality sensitive hashing. So we have not omitted the d is small. So suppose here our space will be, space we have to taken to store this n, to store this n number of points. We have to store this n number of whole points, and also we require the d dimensional space because of that, because of this calculation. Okay, because of this we have to store n number of point and d dimensional, for because of our space complexity for this will be order of nd. And what will be the time complexity to construct this? And the time complexity for each to construct the each slice, we have to take order of nd time, for each slice. If we divide taken the edge hyperplane, just first we have to calculate, just see this thing, we have to compute this multiplications w1 w2 w3 for each data points, so for to compute each data point we have to multiply d number of times, and for n number of points, and for m number of hyperplanes. So for each hyperplane we need to multiply, we need to take time nd, and for m number of hyperplanes, so total time it will be taken m nd. Okay, so for constructing a hash table, okay, this is the for constructing a hash table, this time and this space we have required. And one thing also we have to remember, that number of slice here, number of slice is totally dependent of our number of hyperplanes. So the number of all the slice, so number of slice is dependent on what? Number of slice is dependent on number of hyperplanes. This is the total. This is the simple formula. If we increase the number of hyperplanes, our slice of this plane will be increased. Now the question is, at the end of the day we have to find the class level of a query point. This is the simple task for every classification, so any simple, or for any machine learning algorithms. For a query point we have to find its output. So suppose let's take here our query point is here, query point is here. Suppose let's take our query point is here, xq. So how to calculate its output of this query point? So simple, for this query point we have find the hash value, just for this simplicity, for this query point. Suppose let's take a hash value, we have to calculate the hash value of this query point. How to calculate it? So simple, we have to multiplicate it xq to the edge wi. So we easily can construct. So the hash value will be like this, 1 2 up to n. This will be our hash value of this query point. Suppose let's take this hash value is actually, this hash value is, suppose let's take we have considered the number of 3 points, 1 2 3. So the hash value for this point is 1 1 1. Suppose let's take this value is, this hash value for this query point is 1 1 1. And so if this hash value for this query point is 1 1 1, and then corresponding output we can then, if the simple, this hash value means what? This hash value means simple the key of this query point. If we easily got the key, then we can corresponding got its value. So what will be the value? So the h of xq as the key in the hash table, then its corresponding value will be, so in corresponding value will, how to get the simple formula, d, if we call this table as d, if we call, so d dot, this value will be d dot get of h of xq, means what? If we take this hash value for this query point is 1 1 1, means d dot get of 1 1 1, this will simple give us this output x1 to x5. This will simple gives us this output x1 x2 x3 x4 x5. This will simple give this output for this query point xq. Okay, so now for a given for a given query point, what is the time complexity to count the highest value of a query point? So suppose let's see, so for a given a hash table, we have see the time complexity and space complexity to compute a hash tables. Now what is the time complexity to find the hash value of a query point? Let's see. So for a given hash table, the time complexity for a query point. For a query point xq is what? So we have to calculate it. The h of xq means what? If we consider our taken the m dimensional hyperplane, if we consider the m dimensional hyperplane, then how much calculations we needed to calculate this one means if we have d-dimensional space, so we required for h calculations we require d such kind of multiplications, here also d such kind of operations, here also we need d such kind of operations, and we consider what number of points, m number of hyperplanes. So we need our actual order of our time complexity for calculating this has value is order of md. Okay, I think you will understand this thing. For each point, if we were d-dimensional point, and for one query point we required d number of operations, for m number of such planes we require md number of, so its order will be order of md. So if n dashed elements in this bucket, suppose let's take for each slice we have we for to calculate a total time for query point, the hash to calculate the hash value for a query point we require order of md number or md time. Suppose let's take xq is belongs to n dashed number of slides. Suppose let's take here in this case, that is slice 1 I am taking. For clarifying, I am taking these examples. So just don't be confused about the general term and this term. Just take these examples. This example I am taking this example. Suppose let's take in this slice we have n number of points. Denoting it here. Suppose let's take in this slice we have n number of points. So we have to, at the end of the day, we have to find its class level. Okay, so we have to compare this xq. I am not getting its neighbor point will be these points. If we get this key value a111, then we can conclude that our neighbor point will be this point. But after end of the day, we have to find its output level, means we have to compare this n1 number of points, these 5 points, to the xq. So in such cases we have required also n1 number of comparisons to this point. Okay, so in such cases we have also required, if we have given a xq as a query point and n1 elements, if we have n dashed number of elements in the slice, in this slice, okay, in this slice, if we have n1 number of points, if n1 number of points, then we have to make n1 dashed, then we have to make n1 dash comparisons, then we have to make n dash comparisons, and for this for this comparison we require order of n dashed d time. Okay, so total, so after this comparison we can conclude it what is its majority for these slides, and according to that we have decided. Okay, so now how to total time, what is for a query point, what is total time? The total time complexity now for finding the hash value, it's required order of md time, plus for deciding its output level we require n dash d time. Okay, if n dash is very small, because actually we have originally see if our m value is increased, that implies what? N dashed value is decreased. If we increase the number of hyperplane, this slice will be smaller and smaller, then number of points in our slice will be smaller. This is the simple relationship. So if n1 number, if n dash is small and if n dash is small, then our total time complexity we can conclude that it's order of md. This is the simple concept. If this thing is, if n dash is small, then this will take you this. But typically, how to choose this m? What will be the proper number of n? How many hyperplane we have to choose? What will be the proper value? But typically, the scientists, the data scientists, the mathematicians, the engineers are taking typically the value is log of n. So typically, the value of m is approximately equals to log of n. Means this is the number of hyperplanes. Number of hyperplanes. And in such scenario, what will be the time complexity to construct this table? So in such scenario, the time complexity, so the time complexity to find a output of a query point. So in such scenario, the time complexity will be to find the output of a query point. The time complexity will be order of md. Enter m means order of a log n, so this thing will be simply d of log n. If typically you have taken m is equals to log of n, this thing will happen typically. Generally, the scientists are taken this thing. I think you have understand how to compute the output of a query point by using this locality sensitive hashing. I think you have understand. Now there have a one main major problem. So let's see what is the major problem of this scenario. Suppose let's take this is our sample a hyperplane, and this is for responsible for features 1, this is responsible for features 2. So suppose let's take these are to our hyperplane. Suppose let's take this to our hyperplane. This is pi 1, and let's take this is pi 2. This is pi 2. Okay, and suppose let's take we have a query point here. Suppose let's take we have a query point here, exclude here we have a query point. Okay, so from this table, from these discussions, from the above discussion, we have seen that all the point of this slice, means slice 1, this is slice 1, this is slice 2, this is slice 3, and this is simple slice 4. So the query point if here, so from the above discussion we will see that this query point neighbor points we have taken this slice 1, the neighbor point we have taken the slice 1, but actually if you just see, if we have a point, suppose we have a point x, suppose let's 20 is here, so we can avoid this x20, but it is the closure of this query point. Just see this thing, this is the closer point of our query point. This x20 point is the closer to our query point, but we are simple omit this point, we have not calculated. We have just simple taking this slice number 1. So but it is not actually true thing. So how to avoid, how to resolve this problem, how to just there have a simple hack. Just we have to use a simple trick here to avoid this problem. So the problem is here, just write down the problem. So the problem is if x20 is very closer to xq, so in such scenario we could miss NNN in the cosine similarity as your measure. So in such scenario we could miss a nearest neighbor point in cosine similarity in cosine similarity as in our measure, as our measure. We have simple missed this point. So to resolve these things, we have simple, without repeating this process, we have repeating this process m times, so simply l times randomly. So how we'll do that? So first we have taken, suppose first we have taken a hash value by taking n random. Suppose we are considering a randomized, randomly generated m value, first, and we have taken the a has, we have find a hash value, hash functions by simple using with these calculations. Just I have discussed here. Just first I am generated m random value, and corresponding this m random value we have find a hash functions. And suppose let's take these hash functions, which look 0 1 2 up to m minus. We have generated this hash table first. This hash table. The next step, we are doing the same job. Again we have randomly generated m value, and on according to this m value we have constructed another hash functions. Suppose let's take this locality is our another hash table. From these hash functions we have constructed another hash table. Let's take this is the hash table 1, this is the hash table 2. We will constructed this hash table 1 from this hash function 1. We have hash table constructed this hash table 2 from this hash function 2. Similarly, we have repeated this job. Suppose let's say we have repeated this job to l times. Again, we have randomly here generated m value, and again we have considered l as functions. Zero, 1, 2, suppose a minus 1, and suppose let's take its hash table l. Okay, just I am repeating l times. We have constructed here how much hash table? So we are constructed l hash tables. By repeating the same thing, because we have taken this we have selecting the number of hyperplanes randomly for each time. So I think this value will be divided like that. So suppose first this is our simple hyperplane. Suppose first I am taking this hyperplane. In the next step I am considering suppose like that hyperplane. In the next step I have taken this kind of hyperplane. In the next step we have considering this hyperplane. So if our xq point is here and x20 point is here, I think one of this randomized time these 2 points will be lie on a same chunk. Suppose just to take the white partitions, this white partition. Just take the first white partition. If we consider these white partitions, then xq and x20 are not lied on the same chunk. But if you just take the this red partitions, then in these red partitions xq and x20 will be lied on the same thing, on the same chunk. So I think if you just randomly selected our m hyperplanes randomly for l times, I think one of these times these 2 points, these 2 neighbor points will be lie on a same chunk. So we can easily remove this problem by considering this thing. So we can conclude that for a query point we can conclude that for a query point xq, we can conclude that we have first construct a first hash value for this query point h key, and according to that key we can construct a hash table. We can construct a hash table 1, and suppose let's take we have finding this value x1 x2 x3, suppose let's x2, and in another step what, just to repeat this thing again randomly, these things again randomly, we are doing this thing again randomly. Here I am considering the another hash function corresponding key also we have. Here we have construct a hash table 2, and suppose let's take we have constructed array has h2 h4 h suppose 19 h suppose 5. Okay, for this hash value we have, so the same thing also we are repeating for l times, for l times is l of xq. Similarly we got its key and we have find this hash table l. Similarly we can got some values. So after end of the calculations, l calculations, we have to union this, we have to union, take the set of union of this value. We have to take the set of union of this value. So this value set of, if we just take the set of union of this value x1 x2 x3 x4 x5 x19 x20, now I am considering this will be our neighbor point of our query point at the end of this step. Then this problem that C will see this thing, this problem will be now removed from this simple hack. From this simple hack this problem will be removed. I think you have understand this simple thing. Just I am repeating the above thing, just we have taken the calculations from the above thing l times randomly, just to remove this thing, just to confused about this thing, just to remove this problem. This is the simple hack. Now the thing is that what is the time complexity for these cases? So the time complexity now for these cases will be, so the time complexity to a query point, xq for a given l hash table. Hence here we have given l hash tables, we have calculated the l hash tables for a given l hash table. L hash table is what? For calculating one hash table, how much time we have needed? How much time? Just see this thing. So calculated one hash tables, we need to take how much time? Just see this thing. Yeah. So we have taken order of m n d, or simple order of to calculate it a simple one hash table. We need the time order of m n d. So to calculate the l hash tables here, how much time we have needed? We need to complexity to calculate this l hash tables. We need how much time? Order of l m n d. This time we have needed, because to calculate one hash table we need this time, this much time m n d, and to calculate this l hash tables we need simply L of n or d. Now to time complexity to a query point for these L hash tables is what? So the time complexity in such cases for a single query point, for a single table, for a single hash table, so how much time complexity? Just see this thing. So the time complexity is order of md. For a single hash tables, we have calculated L hash tables. So the time will be order of L of md. This is the simple time we need. If in general if is small, in general L is small, we can repeat this thing in some small number of times. So we can easily conclude that if L is small, this time will be order of sample empty. Okay. So the conclusions of this thing is, as the number of hyperplanes increases, this means that number of slicing increases. This means that number of points per slicing decreases. This is the simple thing. This is a simple trick. Okay, I think everything still now. I think this is so long lectures. So I think if you are just boring it, please pause this and just press it up and then again rewatch this thing. I think it is a simple thing, just simple extensions of the hash table, just uses of the hash tables. By example, the cosine similarity we are used here to find a hash, to build a hash table. This is a simple primary concept, and we are doing some mathematical trick, we are doing some hacks to solve some issues, to resolve some issues of our data sets. Okay, I think this thing is clear. I think this is a so long lecture till now I am also boring to record these lectures. So although if you have any problem, please comment below, or I think just pause it and refresh from outside, just, and after that you will watch again this video. I think after that this thing will be clear all of you. Although if you have any problem, please comment below. I will try to give my best. Okay.